Good morning, everyone. Thank you for joining this morning. I see that a few people are still joining the meeting, so I think we'll give just one more minute for everyone to join and then we'll start. Okay, I think we can start with the introductions while we still wait for people to join. Thank you again for joining today for this wonderful session. Today, our speaker is Dr. Dylan Zeiss. I'm going to quickly read his biography for you and then give you a few, say, technical details of how the meeting will proceed. So Dr. Zeiss has completed his undergraduate and postgraduate studies at the University of Johannesburg, obtaining a PhD in biochemistry with a specialization in plant metabolomics and analytical chemistry. During that time, he published several articles in internationally acclaimed and accredited journals. Following his studies, he moved into industry, joining the Waters division of Microcept as the high-resolution MS application specialist in their team. His expertise is focused on LC-MS-based metabolic profiling. Thank you so much, Dylan, for taking your time today to do this insightful presentation. I also want to say thank you to Metabolomics South Africa, National Metabolomics Platform, Microcept, Diplomics, Northwest University, and UJ, who all work together to make this possible. And especially thank you for you attending. We're going to take the questions after the session. So we're going to give Dr. Zeiss a chance to do his entire presentation, and then you can have a chance to ask your questions. So you can either type the question in the chat box. You'll see that there's a chat box, and you can type your question there. There's also a Q&A section there where you can type your question. If you really feel that you have a difficult question, it's going to be difficult to type it in one sentence, you can put up your hand as well. You'll see that you have a raise hand option there at the bottom. If you do raise your hand, we will unmute you and then you can ask your question live. So for today, we have the three panel members as well. So the thought here was that the panel members all have different backgrounds and different expertise in metabolomics. And so if you ask the questions or there's a discussion afterwards, then we can have the panel members also assist. So as a quick introduction, Aurelia and Fidel, maybe you can just unmute and show your face for a moment. So there you go. That's Prof. Aurelia Williams. She's associate professor at the focus area for biomedical and molecular metabolism research. In short, it's Biomet at the Northwest University. She's also on the board of directors of the International Metabolomics Society and the deputy chairperson of Metabolomics South Africa. Thank you, Aurelia, for taking time to join as a panelist. And then we have Dr. Fidel Tigizimana. He's the director at the University of Johannesburg, yes, Research Center for Plant Metabolomics. He's also the chairperson of Metabolomics South Africa. So thank you very much, Dr. Fidel, for taking your time to join today as an expert panelist. I'm joining from the Northwest University as well, from the National Metabolomics Platform. I also represent Diplomics. There you go. So that's the introductions. Please feel free to type your questions in the chat during the talk so that you don't forget. If something comes up, you can immediately type your question, but we will only get to answering the questions after the talk. Thank you very much, Dylan. The floor is yours.
Okay, let's just get this sorted. Please let me know, can you see my
Yes.
presentation and you guys can hear me? Great.
Perfect. Thank you very much.
Okay. You just get my laser, that works. Okay. So good morning, everyone, and thank you again for taking the time out to attend this talk. As said before, my name is Dylan Zeiss, and I am the MS Application Specialist at the Waters Division of Microcept. So for those that previously recall, this lecture or this talk that I'm giving now was actually set up as two parts. The first part was done somewhere last year, I can't quite recall the date, where the focus was on sample prep, moving to data acquisition strategies, acquiring your data. And we're kind of now moving on to the second half of that, moving forward. But before I do jump into that, I just kind of wanted to share this, that for these lectures, the reason why I'm assisting on us and doing these lectures, I have the goal that I want to try and demystify the steps and the intricacies involved within the metabolomics workflow. So that's the first thing, the focus that I want to have for these lectures, for these talks. Second, I know that metabolomics is growing quite rapidly in South Africa, and providing a bit of guidance, I think, can really go a very long way. So the second one is really to provide this foundation of knowledge from which the MSA community can draw from to improve their own existing workflows, their own metabolomics experiments, and then also to encourage new researchers to not just use metabolomics in its own right, but also in conjunction with other experimental workflows that we can slowly work towards a systems biology type view. And then third and finally, this is a bit of an ambitious goal of mine, is to develop the skill and knowledge of the metabolomics community in South Africa, in Africa, such that we can reach a level that we become global leaders in the field. As somebody in industry that works with the instrumentation and sees a lot of the customers working in metabolomics, I know we have the facilities, we have the instrumentation, we have the knowledge, we have the capabilities. I think we're at this tipping point where we just need to put in a bit of the work and really start accepting that we really are experts in this field. So with that, as said, the second half of the talk will be involved with once our metabolomics data has already been acquired and how we, or what steps we follow stepwise to derive meaningful insights from that. So we'll go through the data processing workflow and then show what type of results we get at the end of all of that. And again, before I jump into the presentation, something else I would like to challenge the viewers, the people watching, I would invite you guys to just pick one step within this workflow that I'll be explaining, whether this is feature detection, statistical analysis, metabolite annotation, or the pathway profiling, and just really zero in on that. Just focus on that. And by the end of this presentation, I would challenge you to not only recognize that that's a step in the workflow and that's its purpose, but also to try and explain to yourself how it contributes to the overall workflow. So that's it. Just try remember one thing. That's my request. Okay, so starting with our data processing, something that a lot of people really don't like moving back to, but we start with our biological aim or our directive, why we are doing our metabolomics experiment. It does seem simple, and yes, I understand that excitement of we want to take our data and we just want to mine it for clues that would support us in our biological hypothesis so that we can find the answers we're looking for. But in the context of metabolomics, what does that truly mean? And these are the points that I would like to help you unravel at least. So first, we want to identify the specific metabolites present in our samples under certain conditions. I think that's quite straightforward. We want to quantify the abundance, the levels of the metabolites that we have in our samples across our different sample groups. That's the second one. We then subject our data or our sample, our data to statistical analysis, where we scrutinize the differences that we might be seeing in our data that could be biologically significant. We try and classify or group those identified metabolites so that they can be mapped into known metabolic pathways. And finally, we relate all of that information back to the biology, to the science, to interpret what we are seeing. From a metabolome perspective, sometimes these may be very subtle metabolic flux shifts. Other times it's an entire metabolic reprogramming that we could see. But importantly, from these insights, we generate hypotheses that can be tested and verified by future generations and scientists, right? So metabolomics is really a data-driven science that is hypothesis generating rather than testing. And I would emphasize the point that just because we do not initially know, it kind of feels like a backwards workflow. But because we do not initially know which metabolites are truly going to be in our data, it does not mean that we should be cutting corners. That is tantamount to bad science, and it does give metabolomics a bit of a bad name. And this is why I would like to really demystify the workflow and unravel it so that you guys have a bit of a framework to understand what the steps are. So in the typical workflow, that is now post data acquisition, in theory, we would follow the following steps that you guys can see here. We have now acquired our raw LCMS data. Embedded in our data, we have chromatographically resolved signal peaks that were detected by our MS system. We're assuming in this case, we are performing untargeted LCMS-based metabolomics with LCMS as our analytical platform. The steps we follow is first, we want to assess the quality of our data. And I'll go into each of these steps. We'll move into them into more details as the topics of the presentation. Followed, we would then want to do some optional correction to our data, possible data conversion if necessary. Following that, we would take our data and we would then perform feature detection, where we really extract, or I'm going to be taking Fidel's word, mine the true signals, the true LCMS peaks from our data while selectively trying to remove the noise. And really, I remember, following feature detection, I remember when I started my first metabolomics experiment in honors, I was excited, I received my data, and I just tried to start identifying compounds left and right. And that was unfortunately the incorrect workflow, which we'll get to. But please be better than me. And remember that because metabolomics is a data-driven workflow, we use the data to guide us. And this is why we first perform statistical analysis to show us the overall picture of the data, as well as give us guidance or point us to which peak signals, which LCMS peaks we should first focus on identifying. From there, then we move into our metabolite identification or metabolite annotation. And due to the advances in science, in software that we're seeing in modern day, we also have a lot of tools at our disposal that we can use, a lot of flexibility and versatility. We have things like molecular networking that can assist us in taking on the role of metabolite annotation, and molecular networking can also assist the more advanced researchers in identifying these more complex and yet still unknown metabolites that are out in the world. From there, finally, we can do some pathway profiling where we plug all our metabolites into that we have identified into existing pathways, and that gives us our biological context from which we can now start putting our results together and generate this hypothesis of what we believe we are seeing in our data, in our results. So this is in theory the workflow, the post-data acquisition workflow that we should be following. In reality, we often get something like this. And the reason I added this is there are a lot of new people coming into the field of metabolomics, a lot of people that I've helped, and I've seen this is out of experience, where once they have acquired their data, let's say it's a scenario where you've sent off your samples to be run at a facility and they send the data back. And once you know I have this data, it's a bit overwhelming as for you as the researcher to understand what comes next. How do you go about processing your data? How do you convert this data into some meaningful insight. And especially when we are not following a structured workflow, when we are touching a bit on the annotation, then moving on to molecular networking because it's interesting and it's the new thing. Then remembering, oh, we need to do statistical analysis. We can kind of get sidetracked, deviate from that biological aim that I initially spoke about. And sometimes we get stuck in the middle. Sometimes we linger on some of these steps for a bit too long. Now, why can I not move my mouse? Okay, it's fine. So the first step in that workflow, as said, is we assess, correct, convert our data. I'm just going to put my little mouse here. Okay. So prior to starting our data processing, it is truly important for us to inspect our raw data and assess the quality with which we are working with. The reason why I'm adding this in is oftentimes we do not, as students or as people that are not well versed in metabolomics or LCMS or analytical workflow, we do not go through our data through the processing workflow. We get excited, we have our data, we start annotating, we start doing statistics, and 3 or 4 months into it, we then realize that something's missing or our data might be largely incorrect. And we've wasted a lot of time, we've wasted a lot of resources trying to put these things together. So this is why it's important to, at the start of it, when you receive your data, whether you have an in-house instrument or you're sending your samples out to be analyzed, once the data comes back, that you make an assessment of it so that you know the quality of data that you're working with. And because for this talk, I'm explaining it from an LCMS perspective, where we use LCMS as the analytical platform, we really want to assess our chromatography, which is our one dimension from a chromatographic perspective, but also from a mass spectrometry perspective. So from a chromatography perspective, we want to have a look at the elution profile across our samples. And what I mean by that is we want to make sure that largely, this is not always the case, but largely, that we have the same ions that we can see eluting off the column at the same retention time. We are basically looking for consistency. This does not have to be for every single peak, because often you do get differences in the metabolome between control or treated groups or different types of groups in your experiment. But we are looking for some sort of consistency, something that tells us that our chromatography ran consistently over our sample batches. Next, we want to check our baseline noise intensity. Often, when our LCMS system is really running at its highest level, we can obtain at least 4 orders of dynamic range on a high resolution system. If the baseline noise is too high, or we see it increasing across our different samples over time, this can be an it can be an indication of multiple things, but I just provide a few examples. This can be down to sample preparation, which was not done to a sufficient level. This can also be the LC method setup, which was not quite correct, where we did not have column re-equilibration. This could be down to the mobile phases or the solvents that we used during the run. But these are the things that we want to check. We want to monitor that baseline noise, because if it rises too high, we run the risk of 1, losing low abundance metabolites, and 2, during our integration or our peak detection step, which comes maybe 2-3 steps later, there we have a problem with integrating or introducing noise into our statistical data. Okay, so that's from a chromatography perspective. We want to monitor our elution profile. We want to check the noise. There are a whole lot of other things if I ask my analytical chemistry colleagues, but for now, we just focus on the main important ones that you really have to focus on. From a mass spectrometry perspective, this is quite important. You would open your spectral data of any random peak to check the format of the data. And when I talk about MS data format, it can be one of 2. It can either be centroided data, it can be continuum data. It's almost like a status of your data. Continuum data is our truly raw data, when we still observe like a Gaussian shape peak in our MS spectral data, while with centroiding, we apply, or during acquisition, there was a weighted average applied to the peak intensity, and that results in this stick or line view that we are typically used to when looking at MS data. But the point I'm hammering home is you should know the status of your data. Certain software, or during the data acquisition procedure, certain softwares would want you to acquire it in a certain format because they use that format. Others would want it in another one. And it's not to say it's a train smash. Continuum data can be converted to centroid, but it is important to know that centroid cannot be converted back to continuum. So these are just things to keep in mind. And something small like this can often be a problem where you are trying to import your data in an open source software such as MZMine, MSDAL, and you're just struggling with the processing, things are not working, the software is just throwing errors left, right, and center at you. So it's important to assess this so that you are aware of it. Next, and finally, we want to check our mass accuracy. Depending on the LC-MS system being used, this can either be done by checking an internally acquired, what's known as lock mass. Sometimes during data acquisition, the mass accuracy has already been corrected and implemented in your data, and this is where we get to our centroided data. Other times, it is applied afterwards. I do also know of some researchers that go about spiking an internal standard in their samples, and this internal standard elutes separately from other peaks. And what's really nice about taking this approach is we can pull the elemental composition to check the identity of the standard to confirm it. If that can be confirmed, we know our mass accuracy is on point. And interestingly enough, is if we have that internal standard and it elutes at the same retention time over our samples, that's also a very good indication that our chromatography was running really well. So internal standards, really great. On the negative side of things, if we assess our mass accuracy and we see it's not correct, it has not been corrected properly, or something happened during the data acquisition, unfortunately, the data cannot be used and will need to be run. I'm sure if we really try hard, we can try and find some sort of usage for it, but largely the answer would be the data would have to be rerun. And this is because if the mass accuracy of the MS system was off during the data acquisition, all downstream annotations will inevitably be incorrect. So it's important that these checks be performed, and especially if your samples were sent out and you're not quite aware of who ran the samples for you. After initial data assessment, we now move on to the correction or conversion. Something that I have started incorporating into my metabolomics workflows is converting the raw LC-MS files into a standardized open format. For example, .mzml. If you check and your data has been acquired in continuum mode, remember that some lockmass correction and centroiding step would need to be performed before this conversion. As said, most open source software such as MZMine, such as MSDAL perform best when they use centroided mass corrected data. And the reason why we want to convert our data format to a more open source format is because this gives us flexibility and leverage between the different softwares that we can use, each having their own unique strengths and values that they can provide us in our research. Whether this is Progenesis QI, which can be used with its streamlined interface and has powerful annotation capabilities, or using GMPS for molecular networking with MZMine, because all the feature detection can be done from a wizard where it all runs really quick and smoothly, using things like Metabolomics, Simca, Easy Info for your statistical analysis. It's really useful having an open source format that you can plug into a lot of different softwares. And then something I would also recommend is, if possible, and oftentimes the operators do have a software that allow this, is to compress your your original raw data files to manage their growing size. Modern high-resolution systems can often run data sets into the gigabytes, and much of this data within our files is low-intensity noise, background noise. And by setting appropriate thresholds, intensity thresholds, we can eliminate a lot of this background noise, dramatically reduce the file sizes without losing meaningful data. So that's just something I would add. Okay, on to feature detection, the first truly important step when we come to processing our data. So now that we've checked the quality of our data, we're going to start mining it, and we're going to start extracting information to provide the answers that we want for our hypotheses. The first step in processing our metabolomics data is what's known as feature detection, also known as feature finding, peak picking. There are a lot of synonyms for this. So if I use these interchangeably, my apologies, but oftentimes I call it peak detection. Now, this is right around the time where our brains shut off because we know that math is involved. And to kind of circumvent that and make this easy to understand, I would start with the question of why. Why do we perform peak picking, peak detection? What's the purpose? And the answer to that is because we want to identify and quantify the individual LCMS peaks within our data that correspond to distinct chemical formulas or chemical compounds. And we do this by performing peak detection. We isolate these peaks within our data. One, we can start reducing the complexity by filtering out noise and start focusing on these true LCMS signals. Two, we obtain precise retention times and mass to charge values, which are absolutely essential for metabolite identification. Three, during the peak detection process, we either generate the peak heights or calculate the area under the peak to obtain some quantitative information about the abundances of our metabolites within our samples across our groups. And finally, all of that information that I just mentioned gets packaged into one readily accessible format that we can use to do things like our statistical analysis or our pathway profiling downstream in our workflow. So in math, we have what's known as integration. And basically, integration refers to calculating the area of a various shape. And we all know if we want to calculate the area of a circle, we use the formula of pi radius squared, right? Easy. Very similarly, for a triangle, half base times height. But now it poses the question, okay, so how do we calculate the area under the curve for a Gaussian-shaped peak, like an LCMS peak? And the answer to that is we use, well, the name of the formula is known as apex track peak integration. This is the formal term. I won't go into it, but this is the start of our peak detection. We want to calculate the area under that Gaussian-shaped peak. Now, often in chromatography, due to biological variability, due to our samples, we get coelution. We get chromatographic conditions that our peaks are not quite Gaussian shaped. And as a result of this, this is where we start with step one in feature detection. We apply smoothing. The only purpose for smoothing is to make our LCMS peaks more bell-shaped curved, so that when we apply our integration, that apex track formula that I mentioned, that our integration or calculating the area under the peak becomes more accurate. It can be performed more accurately. Following that, we start matching all the peaks of we start matching all the peaks that we find within a sample, and then we start retention time aligning all our peaks that we found across all our samples to ensure that we are matching the same peaks across each sample. Yeah, I have a little diagram just showing that. It's where we start shifting retention times. In peak detection, there is a bit of leeway that we can accommodate for. If our retention times are slightly out, we can always accommodate for that. But again, going back to that assessment of our data, when we have massive chromatographic shifts, our peak detection will not be able to recover that. And that does become problematic. Okay, and then following our retention time alignment, all this information, all the peaks that we have detected, we have smoothed, integrated, and calculated the area under the curve, or peak height, gets put into this, what I call a metabolite data matrix. So in short, peak peaking turns our raw spectral data into a very structured list of meaningful, what's known as features, because we're moving into the statistics, but we can call it our LCMS peaks, which we then use to perform statistics so that we can get some robust biological interpretation. So the first section of our feature detection, that was our first section. What type of result would we want out of that step? Following that, the main result or the main information we want to get out of that is our sample matrix, our data matrix. And it looks something like this that I'm showing to you. For now, we don't have to focus on the specifics of this table. I do know death by slide is a thing. I would just like to show you selected aspects that I would then also check once I've generated this matrix. When you get to feature detection, you can always reprocess the data. And it's important that you do so that you get the most optimized version. Because again, if mistakes are made, this can cost you downstream. And I'll go through some of these steps that we'll monitor. So firstly, we would check our samples on the rows that I'm showing here. We would want to check that all the data files that I submitted for feature detection are present in that list, in that table. If not, this could indicate that something went wrong with the processing. There are softwares that I know of that will just continue processing even if there's an error. That something could be potentially wrong with the raw data file itself. That is also possible. And then just to preempt you, a fun fact that in multivariate statistics, which is our next step, our samples, which are on the rows, are now called our observations. Next, we would want to assess our peak signals that are in our data. We can now see we have our masses, or what's actually mass to charge ratio. We have our retention times, and depending on the type of software you used for your peak detection, sometimes you get this retention time accurate mass pair, which is quite useful. And I'll touch on a few more parameters or things that we have to check on that now, but just put a pin on that. I will now move on to the next section, and then we'll quickly move back to that. Next, we would want to check our data matrix itself, which represents the peak area, the peak height of each detected peak. So we can see this is our sample, and we can see all these peaks were identified in that one sample, and these are the area under the peaks for each of those. We would want to check, assess the entire matrix for a couple of things. Well, one is the prevalence or how intense the number of missing values or zero values we have. The reason I added this is we can see here in this one table, we have a lot of zeros and just a few cells within the data that did record an area under the peak. Something like this, we should assess, go back to the raw data and see, is this a legitimate peak, or is it possible that our feature detection parameters need to be refined? Something like this, if you do experience way too many zeros within your statistical or in your data matrix, this could indicate either too high threshold parameters set or similarly too low threshold parameters that were set during the feature detection. I'll quickly explain that. If the parameters were set too high, any low abundance peaks that are below the limit of detection would just record a zero value. If by chance in some sample that intensity was above the threshold, that is the only one that we would end up seeing in our data matrix. So that could be the scenario when the parameters were set too high. Conversely, if it was set too low, we can start cutting into the baseline noise of our LCMS data. And during the peak detection step, our software is going to try and peak detect and then retention time align noise, which it's not going to be able to find. And we're just going to start getting a lot of zeros, a lot of missing values within our data matrix, which is not a good thing because it skews the statistical analysis. Next, depending on the experiment or the biological question being asked, we may want to apply some sort of normalization or scaling to make the comparison between our samples more comparable. And then, if possible, and unless it's truly linked to your biological question, we should process the data in such a way as to remove isotopes from the data matrix. This is known as de-isotoping. Again, I show the example where we have a mass of 1076 and then 1077. We can see they're at the same retention time. This could indicate that the isotope itself was placed in the data matrix. This is something we don't want unless it's truly linked to the biological question, because once we do our statistics, during the upcoming statistics step I'll show, this can kind of skew the data, leading to false positives, sometimes negative correlations in the supervised statistical methods. In layman's terms, the statistics will determine that isotope to be of significance, of statistical relevance, of being able to be a candidate biomarker. And then once we get to the annotation step, we realize it's an isotope, and the true molecule, the monoisotopic peak, is not statistically relevant at all. So that's just something to check. And then finally, and I remember now I actually had that. Finally, we would want to perform some sort of blank subtract by removing the blank samples from our rows, as well as removing any peaks in the data matrix that were found present in the blank samples that were also shared in our biological samples. That's also then just a good practice to try. So that was our feature detection, and the major result that we would want from that feature detection step is a Excel data matrix that has been cleaned, that has been pre-processed, that we can now move on and submit for statistical analysis. So moving on to the statistical analysis step, in metabolomics, we often make use of both multivariate as well as univariate statistics, just at different stages of the workflow. In multivariate statistics, we consider, so multivariate statistics is what's known as a projection-based statistical method. And oftentimes the reason we use it is because we consider all the variables, all those LCMS peaks that we saw within our data matrix. We make use of unsupervised methods because it simplifies the data and can show us this global view, oftentimes revealing to us hidden patterns or trends within our data. We can also apply what's known as supervised methods that take it one step further by classifying, or let's say grouping our samples, and then highlighting which variables in those groups are responsible for them being different, which LCMS peaks have the biggest impact or contribute to that differential grouping. And to navigate, okay, so what do we need for our statistical analysis step when we want to perform our statistical analysis? Well, one, we want our clean and pre-processed data matrix. And two, we want a statistical software package that is capable of doing the work. I provided a few examples here of what can be used. Simca and Easy Info are paid softwares, but they work extraordinarily well. If you are brave, you can try and use coding, whether this is R coding, Python coding, SPSS. Those also work well, but tend to be more tedious, and you need to have a very good, solid foundational understanding of the statistics to use that. More often than not, the free, very useful version to use is Metaboanalyst for your statistical analysis. So this was just something that I showed that I pulled from Metaboanalyst. I would highly advise using it if you do not have a dedicated software to perform your statistical analysis, due to its simplicity and versatility. It's really as simple as going to the Metaboanalyst website, starting it, clicking on the statistical analysis, one-factor analysis, and then uploading your clean and pre-processed data matrix. There are often times when the data matrix that you process comes out and is not quite in the format that you need. In that regard, the very quick and simple solution I would suggest is Metaboanalyst can give you like dummy data, tutorial data that you can use. You can open that up and see what the general layout of the data should be. And then just in Excel or Google Sheets, just change your matrix up accordingly. Some transposing or just removing a few columns that might contain sample grouping data or maybe not important. But the real benefit, what's really great about Metaboanalyst is, as said, it's capable of doing the univariate statistics. And this often comes with our t-test, our one-way ANOVA correlation analysis, which is quite useful at the end of our workflow when we have identified the discriminant metabolites that we want to further subject to statistical validation. Univariate statistics works amazingly, and using Metaboanalyst works great. We also have the capabilities of doing our multivariate statistics. Now, I would make the assumption that a lot of people have seen these statistical models. Our unsupervised models, the most famous one is PCA, and then also our unsupervised models such as PLSDA, OPLSDA, and with that, their corresponding loadings plots and VIP plots. For PCA, very briefly, it compresses all your data into a low dimension to allow you this global summary to show you what trends, what shape your data is taking. If there are any groupings, if there are any outliers, if there are any possible batch effects that need to be corrected, if there are any important trends. Something important though is although PCA can show you these differences, it's quite dangerous to make initial assumptions based on PCA alone. It is there to show you the groupings, and based on what it shows you, you would take it one step further to the supervised models, oftentimes binary models, as we can show here with our two groupings, and let the supervised models start assisting us, start guiding us in finding the metabolites that are important to us or in the data. So what I did here is to explain PLS or PLSDA in an analogy that I think would be quite understandable for a lot of people. Because trying to visit the statistics becomes extremely tedious and hard to understand oftentimes. So whether you're using OPLSDA, OPLS, PLS, PLSDA, they work very similarly with to one another, and there are just very minor differences that I'll quickly explain. So let's use this analogy. Let's say we are monitoring, we're at a clinic, we're trying to develop a predictive model that can estimate the chances of individuals, patients getting diabetes based on their blood glucose levels, but we'll be monitoring several other variables aside from the blood glucose level that we believe could be indicators of the disease. And in this case, these are our X variables, our predictor X variables, things like diet, body mass index, physical activity, stress levels, time of day, medication. What these supervised models will do is monitor those X variables, check them, and see which ones have the largest positive and or negative correlation to our very important dependent variable, which is our blood glucose level. We know that's a biomarker of the diabetic disease. We can check the glucose level, and that could tell us, does the person have diabetes or not? So by monitoring these and checking which one of them have the largest effect, possibly a positive correlation, we can start making these comparisons. And in this regard, I think diet, probably body mass index would have the highest contributors. So in this case, this would be an example of PLS. Why PLS? If we call it PLS or OPLS, we are assuming our Y variable, our Y parameter is a continuous, a numerical, or an integer type number. It is not a yes or no scenario or control or treated scenario. It is a physical number that if gets exceeds, or if it is exceeded, or if it's found below, that can have a significant impact in our groupings. So with PLS or whether it's OPLS, that's the important part. Is our biological question linked to a certain numerical, very important parameter? And when we go to OPLS or OPLSDA, that Y variable now changes and it becomes a discrete variable, a control or treated type scenario, or a time trial scenario where it's 16, 32, or certain time points, things like that. And then the difference between the PLS and the OPLS and the PLSDA and the OPLSDA is a signal correction filter. I would highly advise that if you can, rather use the O variant of these models. But in summary, what they then do, what they give us, what the ultimate answer that they provide us is from an unsupervised perspective, our PCA scores plot shows us all the variable, all our samples. Its corresponding loadings plot can show us all the variables that are responsible for the grouping. And that just provides us a global view that we can then use and move on to our supervised analysis. For our PLSDA or OPLSDA, this is truly where we now start telling the software we are grouping our samples into a control or treated scenario or a time trial or different cultivars or different parameters. And we would like it to find which variables, which LC-MS peaks have the highest contribution to them, our groups being similar or being different. And then finally, with our supervised analysis, we also get this really nice VIP plot that can be generated. Well, we can generate the peaks that are important to our data by using the S-plot, our loadings plots, or our what's known as VIP plot, variable importance plot. And there, our statistics guides us to tell us these are the metabolite peaks that we should be focusing because they have the highest statistical significance. They've shown changes within our data. The very important thing that I added here is for unsupervised analysis, like your PCA scores plot, these are results that you can always show. They're really, really nice to show. We can show our scores plot, we can show our loadings plot. For our supervised analysis, we want to show our plots, both scores and loadings, but we also want to validate the models by permutation, by selectivity tests. And again, I won't go into these too detailed, but these can be performed in MetaboAnalyst, which again contributes to why it's such a good tool, great tool to use. And then once we've performed all these steps, we've done our unsupervised, we've done our supervised, we've validated our supervised, we can use the statistics either as our S-plot or VIP plot to guide us on which metabolites we should annotate. So those are our 4 steps as shown there. And really, hopefully, there's this picture now that you guys have in your head that the statistics on the left is telling us which metabolites or which peaks we should focus on. We have our data matrix in the middle, which provides us the intensities of our different peaks across our sample groups, which can be used for some semi-quantitative analysis and can be subjected to univariate statistics later on. We also have our LC-MS data here on the right, which we can go back to and we can use for our annotations, which can help us achieve a high confidence of annotation. And throughout these sources, again, we have our retention time mass to charge value pairs which act as unique IDs, which connect all three of these information sources so that we can very clearly, or in a streamlined approach, navigate through them. Okay, so the statistics by means of the S-plot, by means of our VIP plot, has now hinted to us which metabolites we should focus on. But how do we go about identifying our metabolites? Well, during this process, we are looking, during the process of metabolite identification, we are looking to assign the names, or at least a chemical formula, based on several parameters, the most important of them from an LC-MS perspective being our accurate mass, our isotope pattern, and our fragmentation pattern. When I talk about accurate mass, I am referring to that our LC-MS system is that accurate that we are able to generate these decimal points at the back that we can see. And I will be very honest with you guys, metabolite annotation is intense. It takes up a lot of time, and this is where generally we make the most mistakes in terms of incorrect annotations. What we are looking to do is match this accurate mass that we have to combinations of elements after applying several thresholds, after applying several filtering constraints. The very nice thing about me, or the very nice thing about mentioning these constraints is in many of the modern softwares, they are just built right in. You do not have to be aware of them, but basically what they do is they show you only chemical formulas that you would find in nature. They typically exclude these inorganic formula, which would be incorrect. If you're an inorganic chemist using LC-MS, please be aware of this. And oftentimes these filters would then have to be turned off. But for untargeted metabolomics, they're usually there. And when I talk about applying thresholds, I am talking about our mass accuracy level or our mass error level. So we generate this list of chemical formula based on the elements being used as building blocks, trying to put them together and get as close to this accurate mass as we can. And the chemical formula that oftentimes gets the closest in terms of mass error would be the correct one. So for our metabolite annotation, what would we need? If we have a list or table of our mass to charge ratios or our masses, that's good enough. We can do some annotation on that. It's not the greatest, it's not the gold standard. The gold standard would be that we have our physical raw data that can be imported into a software that is then capable of metabolite identification. And the step that I just explained or described to you guys is what's known as elemental composition. When we cut down or just break down the word, elemental is we select a group of elements that we believe would be contained or embedded in the chemical structure of the molecules we're looking to annotate. And composition is we would like to see how much, how many carbons, how many hydrogens are within our formula. So just to take you guys through like a very basic stepwise guide of how we would perform some annotation is we start with our accurate mass. We have this molecule. This is a mass spectra. And because we can see it as a peak, we know that this is continuum data. So just something to be aware of. There's a possibility that this data was not mass corrected. We can see that this is an ESI positive. And if we know what the ionization was, we can make the assumption that this molecule had the addition of a hydrogen ion added to it. So we would take this accurate mass formula. We would apply a threshold. In this case, I selected a threshold of 1 millidalton, which I think is really a gold standard. We have high resolution instruments that can go far beyond this, go to sub ppm levels. But for now, we have a 1 millidalton threshold. So we can see it will then try and build chemical formulas that are using the elements that I provided there. We can see we have carbon 12, hydrogen, nitrogen, oxygen. really use them like Lego pieces, put them together in combinations to see if it can generate a chemical formula or several chemical formulas that lies within this mass range. The smaller our threshold is, the more accurate the elemental compositions or the formula that it generates will be. The wider that range, the more chance we have of bringing in more formulas and the more formulas we have to sift and work through. So following us setting these thresholds, we can do some calculations from the monoisotopic mass. So in this case, what the software would do, I'm just showing you what the software would do, is to get as close to that value as possible, minus the hydrogen ion. It randomly, this is now where the software does its thing. This is a bit of a black box. It starts adding different elements together in various combinations to generate a chemical formula list. In this case, it used 8 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens, and we got to 194 Daltons. Remember, this is Daltons, and what we see above there is our mass to charge ratio. When we remove the hydrogen ion, that's where we get to it. And when we searched a database, you can just take that chemical formula and just put it into Google and see if you get some sort of hit. We can see that this is the chemical formula for caffeine when we have the addition of a hydrogen ion. So that is those are the basic steps that we would find or use. And this step of elemental composition is the foundation. It is the backbone. It is the very air of metabolite annotation. Yes, we have now gone beyond it where we have softwares that are capable of performing library screening, but those libraries themselves use this structure, use this architecture where we still need to provide it, the software itself, with a list of chemical or elements that we would like to use, with a list of, with a tolerance threshold of our masses. And here on the screen, I just added a lot of the various both vendor and open source softwares that can be used. To my knowledge, all of them do have the capability of performing your elemental composition. Remember, when doing that, you should be aware that the mass accuracy has been corrected. For viewers that do not have a dedicated software that can be used, something I would advise, MZMine works extremely well, exceptionally well, especially if you're able to convert your raw data that you obtain into a format like MZML that is readily accepted. Things like GMPS, MSDAL, and Sirius are also gaining heavy traction, are also quite popular on the open source side of things. That being said, there's a reason we have all these different softwares because they provide value in different ways. They have strengths and they have weaknesses in different aspects. And then here on the left, what I'm showing is the process I just took you through. Or when we get to annotation, there are levels of our annotation. And ideally, what we would like to do is reach level 1, the highest level of annotation possible. Oftentimes, this is not possible, but we can try the best we can. I'll quickly go through those. So level 5 annotation is we have a unique feature with an accurate mass. That is basically coming from your feature table. If you publish on that, somebody else could always use their elemental composition calculator, and they could use that to derive a chemical formula. So that's a level 5. The moment we can create a chemical formula that is very close to what we're seeing in terms of our isotope distribution, our charge, or our adducts, that can be a level 4. So in this case, that was where we generated the CH810N4O2 chemical formula. The moment we can take it one step further and either search a library or go online, search it on PubChem, ChemSpider, things like that, we can push that to a level 3, where we now have a tentative structure or a name to our molecule. But this is really the really important threshold, is for us to really have a good level of confidence in our annotations. We want to push it to level 2, which is known as a putative ID. And this is where our MS2 data, our high energy data or our fragment ion data comes in. So as said, with that, we are now entering this age where there are a lot of online libraries. I will look to share these slides in like a PDF format so that you guys can see, but these are just some of the libraries that I've been able to get hold of, extremely useful. But we can see we are starting to fill the metabolomic space, fill up the metabolome of different biological organisms, and there are a lot of libraries or repositories that have metabolites in them that we can use for the library screening. We have now reached this point where instead of doing generating a chemical formula, doing the structural elucidation manually, we can submit our mass to charge ratios, our MZ values, straight to a software such as MZMine, such as MSDAL, or the vendor software such as Progenesis or Waters Connect, that are then able to import these libraries and do the screening for us, which just leaves us with like a curation role where we can go through the results and check that the work is performed correctly. If you have, for the more advanced users, when you have this level of knowledge, understanding the thresholds, understanding the isotope ratios, the different filter constraints that can be added to make your annotations more accurate, this becomes a very powerful tool to have all these libraries at our fingertips. And then this was one example that I generated for a customer recently that I would just like to show as an example of a level 2 annotation, where we have our molecular ion here. This was recorded in ESI negative mode. I see that I did not add that on the screen. My apologies. We can see we have our molecular ion there, which I was able to link back to the structure. I can also see I did not add the chemical formula. My apologies. But I was able to take the accurate mass, generate a chemical formula, take that chemical formula, put it in a library, whether this is PubChem, ChemSpider. We found this hit on the structure. Obviously, there were a lot of others. But then what was really useful is due to the MS2 information that we had, due to the high levels of mass accuracy, remember I spoke about mass error, we were able to then break the molecule up and connect each of the individual fragments to the pre-structure of the molecule. So this is an example of a level 2 annotation where we have what? 1, 2, 3, 4, 5, 6, at least 7 fragments that correspond to this molecular ion of interest that we were studying. And remember, this is again where we need to keep in mind to the level of mass accuracy that our instruments are capable of achieving. In molecular networking, this is something that has gained a lot of traction in the past few years, especially since once I started leaving university, it became a hot topic. Very briefly, in molecular networking, it's a computational approach where we compare all the MS spectra within our data that we have, and we compare them and we group them based on what's known as a similarity score. In GMPS, it's what's known as our cosine score. If we look at a specific, and we end up getting these various clusters within our network. If we look at a specific cluster, just following the terminology, we have our nodes. These nodes equate to an MS spectra that we have for a particular peak within our data. So those are our nodes, as shown here. We have node A, we have node B. Our edge, which is the connection point between them, there, only gets made if, as said, because of that similarity score, that cosine score, we only get an edge. An edge is only connected between these two nodes if we have some level of similarity between our compounds of interest. And then finally, you can see how we get this giant cluster created, which can highlight to us potential molecular families that we can then start mining or scrutinizing or investigating. And what's really amazing about molecular networking is if you've identified, let's say, the molecule that's in node A, we know that all the surrounding nodes that have been connected to it share some sort of spectral similarity. So by definition, that shows that those molecules, although they are currently unidentified, do share some sort of similarity in terms of their chemical structure as well. And this is really exciting because it can be used, it can be tentatively extended to start identifying the true unknowns. It helps us to accelerate the annotation of new novel compounds. Very brief step-by-step guide. We can go to the website in GMPS, you log in, you create a free user account. From there, we have actually two different types of molecular networking, whether this is classical or feature-based molecular networking. What do we need for us to perform this? Well, one, we need our spectral data. Again, the reason why data conversion to things like MZML or the data format of MZML is so useful. And our feature quantification table in this regard is our data matrix. Depending on the type of software you use, just having your raw data and having that data matrix is all you would need in this regard for classical molecular networking. For things like feature-based molecular networking, there is an additional metadata file that is required that just adds a little bit more information about your sample groups and accessory information, things like that. Once we have selected the one we use, it's really about uploading our raw data files and then specifying just a few parameters. I won't go into too much detail. I'll just specify the main ones. So this is an example of where we specify the minimum cosine value between our nodes. In this network above here, if we specify a cosine value of 0.7, we can see that we create an edge between these two because it has a cosine value above that. If the cosine value is below, like it is shown here, we do not create an edge because it hints that those two MS spectra, which come from two different peaks, do not share structural similarity. We have our top K parameter, which just describes how many nodes can be connected to a single node. In this case, I did not use this 10. I specified a value of 4, sorry, in the says 6.5. So here we specify a value of 4, and this is the reason we see those 4 connection points between them. Here, our maximum component size, it just speaks to how big our total clusters can become. Here, we have our minimum matched fragment ions between our spectra for, and again, an edge to be connected to them. And then very importantly, we have our maximum mass shift, which is reported in Daltons. To my knowledge, if we have high resolution, accurate mass instrumentations capable of going down to ppm levels or millidalton levels, we should truly maybe do some experiment and see that we can push that value a lot lower. I do believe having a mass shift that high can result in a lot of false positive connections between your molecular networks, which leads you to believing that there are structural similarity between two different spectra, when in reality, there are none. The other really nice thing about GMPS, in addition to it providing you a molecular network, it also has the capabilities of doing the annotation for you, again, based on the parameters you specify, where we have our mass tolerance, we have the minimum number of peaks that should be matched for MS-MS, and we have our score thresholds. So you can import, and GMPS does have several really good curated libraries that come in from the community. They can be imported, and as part of you doing molecular network, you can get several really good annotations. I do know within GMPS, there are several plant metabolite libraries. The human metabolome database is present. The lipid maps library is present. So that already covers the human, lipid, and a lot of the plant aspects. I do believe that the natural products atlas can also be connected. So that covers a bit of the microbiology, bacteria, and fungi aspects of it, just to name a few. So once that's been done, sorry, I kind of jumped forward, you would upload your raw data, specify your parameters accordingly. And again, this is why it's important to be aware of your mass error, be aware of the quality of your data. Once that's been imported and uploaded, you would just wait for your data to be processed on GMPS. What's nice is GMPS kind of sends out an email to tell you that the data has been completed, and you have a page, something similar to this, where you can either directly download your graph ML files, where you can import it into Cytoscape to really make your molecular network look nice, or delve into the data to see how two different nodes are similar to one another. Again, I mentioned that retention time mass spectrometry pair, which can be used again throughout the data. That's really important, really cool. You also have this direct Cytoscape preview or download, which I've shown here. But in addition to that, there's a lot more in GNPS that can be done. So the basic key advantages that I would like to leave you guys with when it comes to molecular networking is, one, it scales large data sets. It reduces these thousands of spectra that we have across our samples to hundreds of very meaningful clusters with nodes of our MS spectrum. That's the one. Second, for again, those more advanced metabolomics or identification users, oftentimes it can reveal, molecular networking can reveal novel clusters. When the library doesn't provide a hit, it can suggest that there is something that is truly novel that we can then investigate. That being said, we should be very aware that the data was processed correctly, or we might be chasing shadows or artifacts. And then finally, for those people on the border of getting the feel of metabolomics, but not yet comfortable with annotation, something that molecular networking assists with quite well is it can place unknown or unidentified features within a group where something has been identified, and that kind of guides you for targeted follow-up. The example that I give can be shown here, where we identified this metabolite at the top because it's the core single structure. But oftentimes in biological organisms, metabolites get converted or biotransformed. There's the correct keyword. And in this case, we can see this molecule was biotransformed with the addition of a glucuronic acid. Sometimes it can be conjugated to glutathione or hydroxylated. And in very rare cases, you can have combinations of these biotransformations. If you do not have this really core background knowledge in analytical chemistry to annotate these types of, or be aware of these transformations, this is where molecular networking really helps to bridge that gap. Another quick parameter that I'd like to talk about is mass defect, which is truly useful when it comes to the identification of some biotransformed unknowns. Mass defect, simply described, is the difference between the exact mass of an atom and the sum of its masses of its protons, neutrons, and electrons. Now, that was a mouthful. The example I provide here is a helium atom on the left here, which has a mass of 4.0260 daltons. But interestingly, when we strip it apart, theoretically, and we measure the individual components, we realize that there's a bit of an addition. Where does this missing mass come from? And that equates to the binding energy that is holding our atom together. If we take this one step further in mass spectrometry, mass defect refers to the difference between a compound's exact mass and its nominal mass, the nearest whole number or integer. It is calculated using this following formula, where we have mass defect equates to exact mass minus nominal mass. I provided an example here, maybe that would help clarify a bit. So we would do the exact mass calculation for caffeine, where you guys can see we use the accurate masses of each element, and we get to 194.08.04. We do the same for the nominal mass calculation when we get to 194. When we minus those from one another, we get a mass defect for caffeine of 0.0804. And although this seems quite simple, it's a very interesting chemical property that can be used in the identification process. I'll explain. So for selected compound classes, when we have biotransformations, when we have glucose residue, different things that happen, hydroxylation, prenylations, things like that, the mass Dalton can change, but our mass defect relative to that molecule and then the original do not change. And they then appear in very well-defined regions when we plot a mass defect, as here on the y-axis, to Dalton mass plot. So we can see that this behavior starts filtering out accurate masses of different metabolites based on their groups. We can see that some of the carbon, hydrogen, oxygen containing formulas group into several clusters. What's interesting is nitrogen, I see there are two dots that I missed there. Nitrogen containing compounds have a negative mass defect, and they actually show up on the whole other side of the plot. So just on a direct assumption, I could investigate those with the knowledge that they would have nitrogen in their core structure, just because of the negative mass defect. And then when we go to the extreme, when we have really crazy low mass defect values, this is where we start having these really interesting elements such as chlorine or bromine, sometimes phosphorus or sulfate coming into the mix. So although mass defect cannot help you in directly annotating it, it can give you a hint. By just doing the calculation and seeing what that mass defect is, it can hint to what type of elements are present within its core, this unknown molecule's core structure. Okay, and then we've now gotten to the point where we've done our statistical analysis. We've done our metabolite annotation. As part of that, we did some molecular networking, which kind of supplements or bolsters that. And we now have this list of hundreds, possibly thousands of metabolites. What now? This is now the final step, which is pathway profiling. What is pathway profiling? Very brief. It places our metabolites that we have in our list in a pathway context. It identifies the metabolic pathways or the metabolic routes that have been most affected in our experiment, instead of just showing us single metabolites. In metabolite annotation, as said, we have it gives us hundreds to thousands of metabolite names, but it does not tell us which biological processes are changing. Pathway analysis groups the metabolites into biochemical groups, into pathways, and we now have that transition where we go from a loose list of metabolites to a coherent story that we can see happening in the metabolism of the organism that we're studying. Yeah. In short, pathway profiling gives us our biological context. It brings back the data to the biological context. Secondly, as said, it does reduce complexity where we now move this to the biological process. And really importantly, it can help us now generate a hypothesis by seeing which pathways have been overrepresented or impacted or altered. We can start forming some specific hypothesis and design follow-up experiments more intelligently to test if this is the case. This really saves a lot of time, and rather than chasing down dozens of scattered metabolites looking for patterns or links, pathway analysis highlights the key steps that are affected. Again, really nice. Pathway analysis can be done in Metabolomics. We go to the website, we select pathway analysis, and all we really have to specify is either a list of common names. Really importantly, that the format of those namings, sometimes a human metabolome database ID or KEG ID, but thankfully the software does have a conversion app that can assist with that. We can then take that list, submit it, and there are literally just 4 parameters for the pathway profiling that we have to fill in. The first and the last one hint to how we want to see our data. Do we want to see it as a scatter plot that I just showed, or in a heat map. The last one asks, do we want to use the software's library, which contains the whole repository of the human metabolome library, or it references KEGG, which is quite vast, or do we want to upload our own reference library? We would want to do something like this when we are studying a very specific metabolic pathway. These two in the middle are the really important ones that I would quickly like to touch on because I see I'm running out of time. So rather than saying, okay, our enrichment method is the hypergeometric test or Fisher's exact test, that doesn't mean anything. I would explain it to you guys with an analogy, which I wrote there, but I will explain it to you. Let us say we have a bag of marbles, right? Let's say we have a bag of 100 marbles. And out of those 100, we have 10 red marbles. Now, if we put the marbles in, we shake them up, and we do not look, and we randomly pick out 20 marbles. From a statistics perspective, what should be the norm? How many red marbles should we pick by chance? And the answer is about 2 red marbles, because that's the p-value, sort of, that 10% or 5% of the time that you would pick one of them. And this is now where this enrichment method comes in, where it shows you that when we plugged our metabolites into the pathway, were there more metabolites that we found that were altered in the
Sorry,
pathway?
Dylan.
Yes.
I think
Yeah,
your
Prof.
sound, I'm not sure if it's just me. Is he still audible?
Yes, I can hear very well.
Okay. Can I continue?
Yes.
Okay, sorry. Finishing up a few more slides. The enrichment analysis or the enrichment method really tells us or provides a p-value to show us that we have an above average chance that we have seen more metabolites being affected in a metabolic pathway than what we would typically normally see. That's the enrichment method. For most cases, the hypergeometric test works very well. If you have a very low number of metabolites that fit into a pathway or very low abundance, you don't have a lot of annotations, the Fisher's exact test is more precise to accommodate for this. So for general use, hypergeometric test. For low abundance, the Fisher's exact test. In terms of the topology measure, again, I will use an analogy to explain that. In this case, we would like to think of a specific metabolic pathway as a city. And based on the number of roads that connect into the city becomes more of a hub of influence. And this is very similar now that we're analyzing now. Based on the metabolic pathways that the software finds that have been affected, it can rank them in node importance based on how influential that metabolic pathway is to various other pathways. So the relative betweenness one counts how many roads leave the city, how many metabolic pathways one specific pathway feeds into. The betweenness one counts the shortest routes, how many steps within 2 pathways are required to connect them. So that's just for your knowledge. You can always play around with both and you can reprocess, see what you get. The answer of what we get for our pathway profiling results is we get this bubble plot, which is really nice. We can also generate it as a heat map. We here on the x-axis, we have that impact, as I said, how many pathways affect how many other pathways. And we have this, in this case, it's a log p-value. So it's a reverse of the p-value that was calculated to show that more than the general average of metabolites were affected in a specific pathway. We would then focus on the pathway generally shown in red. But as said, this is dependent on your biological question. That is the one result we can get. The other one is that we get this list showing which metabolic pathways have been affected and altered and how many metabolites we were able to match in the total scheme of each of those pathways. The final one that I have there said is pathway maps, is if we click on these details, this takes us to KEGG, which is the Kyoto Encyclopedia of Genes and Genomics. It's a really amazing website. I used it during my studies. It is a very comprehensive and manually curated database. I have contributed to this database myself, which has a lot of information from a genomics, transcriptomics, proteomics, and metabolomics perspective. It allows us to map genes and metabolites onto known metabolic pathways. I cannot highly recommend the software more, that you go and see it and see the number of metabolic pathways available across various organisms. It's really useful when you're trying to connect metabolic pathways where you have several metabolites and would like to see how they feed in between different metabolic pathways. But really, in summary, what KEGG does is it allows us to explore molecular interaction and the reaction networks. So in summary, I'll run through this very quickly. Those are our 7 steps to processing our data. Yes, there are a lot of minute or more intricate things that I might have missed. For now, this was just a general thing so that people have some sort of strategy that they understand once they have their data, how they process it through to get to the experimental results. The steps include data assessment so that we can check that we have good data that we work with from start to finish. The saying is garbage in, garbage out. We want to perform correction and conversion because this provides us flexibility and versatility in how our data can be processed. Everything hinges on feature detection, and you can always go back and reanalyze, reprocess the data. But the quality of that data matrix, as you guys have seen, lingers on and leaks into every subsequent step within the workflow, especially our statistical analysis, which is there because it should be the one guiding us to our discriminant ions. I know it's alluring looking at your data and saying, oh, I'm going to start with the big metabolite first, or there are a few ones with nitrogen in them because they have even mass to charge ratios. But in a true metabolomics experiment, the statistics should be the one guiding you to which metabolites should be preferentially identified. Metabolite annotation, it's a very big and broad topic. It can be a science on its own. My advice is understand the fundamentals of how we go from an accurate mass to a chemical formula to a metabolite name and everything associated in between. Molecular networking, I would highly advise you guys try it. It is the future. It's only going to become more prevalent from here because it has application in so many different fields, not just metabolomics. And then finally, our pathway profiling, which we use to place all this information into a biological context so that we can link it back to the biology and either answer a hypothesis or generate it for follow-up study. That is everything I have. Thank you for your time.
Thank you so much, Dylan. If this was in person, I know that you would have received a massive applause for that. Well done. It was a lot of information, but you managed to really explain a lot of the things in simple terms and touch on every single thing. We had a lot of questions and answers, and some were already answered by the panel members. Thank you very much. I think just for so to get everyone on the same level, I'm going to repeat some of the questions that were asked, just in case you didn't get to that answers and you also were wondering about these things. So the first question that a lot of people asked is, will the recording be made available? Yes. This was recorded and it will be uploaded on the MSA YouTube channel, the NMP YouTube channel. We will send the link to the YouTube videos to everyone in the all the attendees afterwards. Then again, thank you for taking time to attend this. We had about 110 attendees, and everyone participated incredibly well. Okay. So I'm going to start. I'm going to just repeat the questions, and then any one of the panel members are welcome to also jump in and give different answers, etc. Aurelia, you have your hand up.
Yes, also just we are at 11:30, so I'm sure most people will probably exit by now. So I think There's a few pending questions, so I think, is everybody okay then with staying for maybe 10 or 15 more minutes just to work through those questions? But I do think most people will be logging off soon.
Yeah. Okay, but let's start then with the ones that were not answered yet, and then we go to the ones that we've already answered. Okay. So Evelyn asked a question. I don't understand that question really. It says, could you point out the previous checking in the data set, previous data analysis? I'm not sure, Evelyn, if you want to unmute yourself and just clarify that question. And then not unmute yourself. You can just put up your hand, Evelyn, and then we can unmute you. Okay. The next question is, thank you, Dr. Dillon. I'm new in metabolomics. How do you calculate mass if the peaks have the MZ and the retention time only?
Okay, so you guys can hear me. Yeah.
Yes.
So we usually start with the accurate mass and the retention time, almost as a coordinate system. You would go into your data. You could take your MZML file, load that into something like MZMine. The moment that gets uploaded, you usually have your chromatogram view where you can see all your peaks. You would then navigate to that retention time. And if you like right click and drag or just right click, you get its corresponding spectra, and you then should see the mass to charge ratio there. Usually that's the low intensity or the low energy spectra. So you have your precursor mass. You can do some alteration. I'm not quite sure where the button is now, to obtain the higher energy, and that would give you your fragmentation pattern. That's then your low and your high energy, and you can make use of that for your annotation. The accurate mass to charge ratio is always used for the identification, whether it's the precursor or the molecular ion, or generating a chemical formula for a fragment.
Okay, thank you. I just want to mention now, as Aurelia said, people are going to log off. I think when we send out the recording, we will also send the email and contact details of all the panel members. So if you have a specific question, then you're welcome to send us an email afterwards, and we can also answer. Then from Donald, which software can we use to identify each ion fragment and finally to build the structure?
So I'll type that answer and say it as well. I would use for now, for this, I would use a combination of MZMine as well as ChemSketch. So MZMine would allow you to see your mass spectral data. So that way you can look at the precursor, the fragment ion data. You can use that to generate a chemical formula, from there get a structure. And if you then believe that is your compound, you can draw that structure in ChemSketch, and ChemSketch has a functionality which allows you to break it into pieces to see if those align or are the same as what you got in your data. So that's a combination I would use for the manual workflow. Alternatively, you can just import, if you know what biological system you're working with, plant, human, things like that, you can import a library into NZMine and see if it can give you an accurate identification when it runs through all this already.
Okay, thank you.
Ilse,
So there's two
sorry.
people with hands up.
Yes,
Yeah.
yes.
Yeah.
The
So
hands.
I think let's give a chance for those who wanted to speak or forever hold your peace. There's Yannick. Yannick, you're already promoted, so you're now a panel member and you can just unmute yourself and ask the question. Yannick, Kevin. Okay, Yannick did put his hand down, so not sure. Then there's Ivan Anderson. Nhanyatyu.
Thank you
Welcome
so
to.
much.
There you go.
Am I audible?
Yes, you can
Hi,
continue.
how are you?
Thank you so much to the organizer for this event, and to Dylan. Dylan, please, if you don't mind, on slide 21 and 22, you were explaining how with your platform, you can generate possible molecules, possible, what do you say, formula of the compound.
Yes.
And you narrow down, and by the end, you are able to select the exact one Go to 21, please. The former
Okay.
one, 21.
Tell me, can you guys still see my screen? Okay, that's
Yeah.
interesting.
This is
We can see your screen.
21.
I was not aware of that one. Okay, this one.
Yeah, thank you. Yeah. So after this one, you said with the elementary composition, you can decide what is the exact one. Are you using both on the same software, or you are using different software, please?
So in this case, and to my knowledge, I can just quickly run through them with MS-Dial, with MZMine, with Unify, with Progenesis, with Waters Connect, with MassLinks, with OpenMS. Basically all the ones that I listed. Just not sure about meta-analysis capabilities. That process gets done in one software. That's not a split. I understand your question now that you said, how did I go from the formula generation over here to just selecting this is the correct one? There is a bit of information that I did not add on this list here. And oftentimes when it generates these chemical formulas, it will give you a mass error to show you how far away, or what was the accurate mass that it could generate from each of these. Because obviously, if I ask you, go to the periodic table, count 34 carbons, that's going to be 34. Plus 26 hydrogens, with those decimals, you're going to start getting to a specific number, right? Each of these numbers, each of these formulas all corresponds to 609, but the decimals are just a little bit different. And the one that's the closest, okay, well, depending on how accurate your instrument is and depending on whether it has been calibrated properly or recently, the closest chemical formula to what you're observing on in your data is generally the correct one. So that's one. This is now why I spoke about those applying thresholds and setting filters. The other thing that I did not mention is with the addition of these different elements in combination, your isotope ratios between your peaks start changing, the intensity slightly, but they do change. Oftentimes these softwares, when they generate a formula, they can match it up with what your experimental data is, and that can also be used to give you an indication of which one of those formulas is the most likely option.
Okay, thank you. And the next slide, please. 22.
Okay. Come on. There we go. Yeah.
Yeah. Are you using the same software to generate this elemental composition, or a different one?
From the previous one?
Yeah.
Yes. Yeah. Oh, well, in this case, yes, I did. I was using MassLinks in this regard. Something that I wanted to suggest, but this morning I actually saw it got taken down, but maybe we get lucky. If you type in elemental composition calculator in Google, the University of Leuven, I believe, used to have a standalone software that you could use where you could type in the accurate mass and you could do this on its own, a standalone elemental composition calculator. But in this case, this was, these are little partials, but this was done in the MassLink software, but it would be the same result as in any other software. It should not change. It really shouldn't. If you're experiencing changes in your elemental composition between samples, between softwares, either the parameters were set incorrectly or there is something wrong with the process. Something changed majorly. But if it's the same accurate mass, like I showed here, everything downstream, it will not change. It cannot change.
Okay, thank you so much. Thank you.
Sure.
Thank you, Ivan. Then we have Shivarya. Shivarya, sorry, I'm not saying your name correctly. I know this, but you can continue, Kumar. Let me just see. You put down your hand now. Okay, I'll try to correct that. But then there's a question from Joanne Pillay asking, do you use separate workflows for data acquired with positive and negative modes?
So the answer in bold is yes. Yes, I would. As said, we are doing scientists, and I've seen people do really amazing work where they can combine these, but just staying on the safe side, the answer is yes, they would be separate. The reason being is in different ionization modes, you could see different levels of baseline noise. You have different adducts showing up. Sometimes this requires a bit of a change in the feature detection mechanism. If we go to the annotation stage, with positive mode, we add a hydrogen ion amongst all the other things that can happen, the other artifacts. In negative mode, we remove an ion. If we merge that together, you're left wondering, do I add, do I remove? Is this a positive ion? Is it a negative ion? Is it possible that this ion was attached to a chlorine ion, which you would only see in negative, but you processed it with positive? So for safety's sake, there should be two different methods for both positive and negative. The parameters could be theoretically exactly the same, but you would do two processing steps, one for positive, one for negative.
But essentially the same workflow. Thank you.
Yeah, there we go.
Dylan, thank you for that such a very nice presentation. I'm a very beginner in my metabolomics, and I want to really excel the data analysis. Do you or would you like to suggest me some very good reference materials to excel in this? Any books or something like that?
When you're talking about the data analysis, are you referring to the statistical analysis?
Yes, statistical analysis and also raw data analysis, which gives
would you quickly give me quickly give me 2 seconds?
Yeah.
Dylan,
yes.
I think just for time's sake, maybe we can also send some references.
Sure.
As the panel, we can put some references together and some material, and then when we send the link to the recording, we can also attach some of these, if that would be okay.
Sure.
Okay. I'm just going to quickly see.
Dylan, there was one, I'll just go on, Ilse.
Sure.
There was one question from Evelyn about the number of peaks that you need to fully characterize. Was it a spectrum? Was the question. How many points?
Yeah.
How many points on a peak?
Okay. What just a general question, how many points across the peak you would need?
Yeah.
For semi-quantitative purposes, okay, for absolute quantitative purposes, theory books would tell you between 30 and 50 peak, points across the peak. I think it's a bit unrealistic. In reality, let's say between 10 and 15, 15 and 20. For semi-quantitative analysis in metabolomics, if the instrument's scanning at about 0.1 scans per second, or let's say 0.2 scans, you can easily bridge that. So the answer, at least for semi-quantitative analysis, at least 10 to 15 points across the peak, if it can be done.
Okay. Then there was another question asking, how do you make sure that it's a peak and it's not noise? So there's already an answer there from Aurelia, but let's hear what you want to say, Dylan.
It's always a tricky one because we would have to define noise, but this is now why I say you have this connection between your data matrix, your statistics, and your raw data, that if you see something in the matrix and you're wondering if it's noise, you can go back to your raw data and scrutinize it. Sometimes noise, depending on what you're looking at, noise does not have an isotopic pattern. It's just a single peak. So a lot of the companies have a list of known contaminants, if that's what you mean by noise, that you could then cross-reference to see, does this molecule match on one of these lists? If you go to that retention time and you are trying to find that molecule and you just simply do not see a peak, or a not chromatographically resolved peak, you can then kind of make the assumption that it should be noise. If you see that it found something that's not there, that's below the baseline, for now, I'll say under normal circumstances, because I know somebody's listening, we could assume that's noise.
There was a similar question from someone else as well, asking, how do you know whether it's noise and it's not a low abundant and low abundant compound, and if it's crucial? I think from my side, if you look, it depends on the application. Sometimes if things are so low in actual concentration that it's in noise, you wouldn't want to consider it as a marker because from a biological perspective, it would not really be a valuable biomarker if it's in a low abundance. But sometimes when you do, so if we diagnose patients with metabolic disorders, sometimes you look for something that's higher than normal. So that's relatively easy. Sometimes you look for something that's actually lower than normal. And then you need to understand if you are not detecting this compound or if it's actually below the detection limit of the instrument. Yeah, so I think it's a bit of a gamble, but we try, if we do untargeted work, we try to get that mid path between looking at super low and super high things in the same run. It's quite difficult. But Dylan, your answer about is it noise was a great answer. Thank you. That was just more of the same. And then will the slides be shared? Yes. Is it being recorded? Yes. Okay. So I'm just quickly going through because some has been answered. Technical. Based on your experience, what do you recommend as the standard mass shift? Is it dependent on any factors I should know of before choosing a value?
Can you please repeat that question again?
Based on your experience, what do you recommend as the standard mass shift? Is it
Like
dependent on any factors? And how do I choose a value?
Okay. If you're referring to mass shift in the molecular networking workflow, I'm assuming. So, to my knowledge, that mass shift value, which is in Daltons, I'm not quite sure why it's in Daltons, is related to the mass error of your molecule. It is something it is something very new that I've come across, and I still have to test it experimentally. But the suggestion that I would make, in theory, you should be able to go down to 1 millidalton, 5 millidalton, perhaps even lower to the ppm levels. Something that I still want to test is take a molecular network and slowly process and reprocess it with every iteration, lowering that mass shift down. Because I think it started at almost 2000 Daltons, pushing it to 1000, pushing it to 100, pushing it to 50, 10, finally getting it down to the millidalton level to see if we do get changes. Because if so, then, or at least from what I read in the GMPS description, then that is not a true relation to mass error, and it is something else in the workflow that we need to then be aware of. But then I'll contact GMPS and then actually try and find out what's going on there. So at least for now, I would see the answers, I would see how low I can really push that. Because the higher that threshold is set, to my understanding, the more false positives you are potentially letting in.
Okay. So there was just a load of comments saying thank you. It was very nice, very interesting. Thank you, thank you, thank you. And then there's one question. I encountered a problem regarding feature detection. I ran a pre-processing data with MZMine, but when I extracted the data for FBMN, the MGF format is empty, 0 bytes. Do you know what can be wrong?
I'm actually not sure of that, and I wonder if Adele might have not have been the better person to ask that. Let me just quickly see. Please.
It's the last, very last chat.
Extracted data for feature base, but the MGF format. Oh, when you ran it through feature. Okay. Did MZMine report any errors when you did the processing? Because in that case, it just spat out the file, but something clearly went wrong in the pre-processing. In that case, that's a classic example of an error happened, so it didn't proceed through the process correctly, but it still just generated a quick MGF format just to show that it can. Yeah, there we go. Fidel did answer.
So please check the processing. Okay, then there's a a very last question, and then I think we should just stop the meeting. And you, as I said, you're welcome to send us more questions over email. So this one is asking, okay, Dylan, you already answered it. And then there was just one, but I can't find it now. It was answered very well from Catherine. There it is. So Catherine submitted a publication, and she added her 20 metabolites that's different between the two groups of cheetahs with a diet intervention. And the reviewer said she should add all the metabolites, and she's asking about that. If I can just give my opinion, reviewers are just normal people, and they tend to have preferences. Some people prefer seeing everything. Some people prefer seeing only the statistically different compounds. Some want to see every single step that you did. Some want to see just the answer, like your math teacher in school. So if you receive metabolomics is a wide field, and there's lots of applications, loads of different programs you can use, software you can use, data, stats you can do, and people just have preferences. So whatever you do is not always wrong if you get this type of request from a reviewer. It's just just think about it as it's their preference. What we normally do is we add our data to a repository that's online, that's available to anyone. So then you have all your compounds in that repository, or you can remember you can also add an Excel sheet as a supplementary data. So you don't always have to go and make up a Word document with your 10,000 compounds. You can just add a Excel sheet. But yes, I think if you answer that very well, as Dr. Fidel answered there, and Prof. Aurelia, it's about how you answer that question. Yeah, Dylan, you can also answer, but my thought is just always, think carefully about your reviewers and think of them as people with preferences, things that they like to do.
I think you covered the majority of it. I know in a lot of new or a lot of very strong journals with high impact factors, they have this request that at the end of your manuscript that you state that this data that was used in this experiment was uploaded to a repository such as Metabolites or GMPS's equivalent, which I cannot recall for the life of me now, and that's stated, and you can just provide an accession number where they can then gain access to it if they want to analyze the data on their own.
Yes, it's a prerequisite to actually upload it to a repository. And then you don't have to upload everything. Thank you very much, everyone. I think we might have missed a few.
We answered all of them, Ilse. We managed to get
we
through all
answered
of them.
most of them. As I said, we will compile. We might not send this today, but we will compile a list of maybe reference material or other papers. Prof. Aurelia sent along a paper. Dr. Fidel sent a reference in the chats. So we will just compile all of these things and extra other maybe resources that we have with a link with everybody's email, and then send it to everyone who attended. I want to say thank you again. Thank you especially to the panel members I know you are very, very busy people, and you took 2 hours of your day to be here and to share your expert knowledge with the crowd of over 100 people. Thank you very much. Thank you to Dylan for taking your time, because it wasn't just 2 hours from your side. You had to prepare for this. It was a job very well done. Thank you very, very much once again to you and the Microcept team. UJ, Northwest University, Metabolomics South Africa, everyone who was involved, especially the attendees. Any last words from the panel?
No, just thank you to everybody. And Dylan, it's always very exciting to listen to your talks. Thank you so much. I have to leave for another meeting.
Okay, thank you. Thank you, Dylan.
Enjoy your day, everyone.
Okay, bye-bye.
Bye.